Welcome back. Let's do some practice problems for week 5 of Physics 259, where we were talking about the behavior of electric potential in insulators and conductors, as well as talking about equipotential lines. So this first question here talks just about that, about equipotential lines. So it wants us to find the electric potential differences from B to A, so that's this line here, from C to A, and from C to B. So if we just start with looking at, see if you'll let me zoom. If we start just looking at B to A, we can use this equation here. We can use, so VB minus VA, we're given the amount of work that it does. So this is equal to our change in electric potential energy over Q. And our change in energy is equal to negative work over Q. And we have those two values. So that just gives us, so we have negative, how much do we have? 4.7 times 10 to the negative 19 joules. And these are electrons. So this is over negative 1.6 times 10 to the negative 19 coulombs. And this is going to give us, so that's 4.7 divided by 6.1, and that is equal to 2.9375, which you can see we got in our first part. Now, if we follow the path of C to A, it looks a little trickier, doesn't it? Right? But I want you to consider that these are equipotential lines, these dotted orange lines here. So remember, when we're dealing with electric potential, only the start and end points matter. Not the path. So even though it takes a different path from B, because C lies on the same electric equipotential line as B, it's basically like saying is equal to VC minus VA, right? Because we are going from this equipotential line to this equipotential line. So when we did that for B and A, still applies for C going to A. So that's why our answer for part B is the same as part A. And finally, if we want to talk about VC to VB, because they lie on the same equipotential line, there's no difference between them. So we know when you have a constant electric potential, there's no change, so that means this is 0. Okay, so that is our first question done and out of the way. In this example, we will be taking a look at electric potential using a graph. So we are given the x component of an electric field as a function of x in the graph below, where our scale is set by 20 newtons per coulomb, and the origin is 15 volts. So what is the electric potential at x equals 2 meters, and what is the greatest possible value for the electric potential for points on the x-axis, for which x is between 0 and 6 meters, and what is the value of x when the electric potential is 0? So we are going to use this equation here. So this is VF minus VI equals negative our integral of E dot ds. So in this example, we are already given our VI, which is equal to where our origin is set at 15 volts. And yeah, so we are going to want to find, since these are being multiplied together, if I were to write it out just in a more plain way, you could see that electric field times our x, which is our path in this case, is equal to our electric potential. So that's like saying the area, right? Because we have our electric field in our x-axis and in our y-axis, and our x-axis we have our distance. So we can imagine it as just taking the area. So if we wanted to find from 0 to 2, that would be this area, this triangular area here. So we can just simply do that. So for part A, this is, so we have VF minus 15, and we want to find VF, that's what we're looking for. And this is negative. So we have negative area. So this would be, and our EXS is negative 20. So this is minus negative 20 times our distance, which is 2. And this is a triangle, so we have to divide it by 2. And this gives us, so these twos cancel, so this is 20, positive 20, and we add that 15, VF equals 35 volts. All right, so that is our first question done. Let me zoom out so we can perform the rest of our calculations on the side. So now we want to find our area that will be maximized. Right, so we know that so negative area produces positive electric potential. That's because our negative area double cancels the negative with the part attached to the integral. So with that knowledge, we want to find greatest area under the curve. Because if we use the area over the curve, we don't have that double negative cancellation, so it just stays negative. So we want to maximize what our result is going to be. So in that case, if we look at our graph, that means we would be measuring up to x equals 3. So we're going to do the same thing. So VF minus 15 equals negative, and we have a height of negative 20 again. We have a length of 3 divided by 2. So this is 20 times 3 divided by 2, and this gives 30. So VF minus 15 equals 30. And then when we move that 15 over to the other side, this is VF equals 45 volts. Okay, and finally, for part C, we want to find where the value of x, so at what distance is electric potential 0? So now we want to find a point above the graph between, where we can find our electric potential to be 0. So we know it slopes off flat at this point, so we can expect it to be roughly around that area. And we want that to equal our previous answer of 45 volts. I'm so sorry. So we can first consider this triangle here plus some other rectangle here. So if we start with our first triangle, that's half, and we are reaching positive 20 now. And this is over a distance of 1. So that's our first triangle. And shaded in gray is the rectangle we want to add. So this is plus some value of our distance. So I'm just going to put k for now, minus 4. Then times 20 is equal to 45. So now we're just going to isolate for that constant k. So this becomes 10 plus 20k minus 80 equals 45. This is negative 70 plus 45, 45 plus 70. This is 115. And when we divide, that value of k becomes 5.75. And this is our distance where electric potential will be 0. All right, so that's how you can use your knowledge of integrals and graphs and area to find the different values for electric potential at different points of a function graph. So now dealing with some Cartesian form problems, we're asked what the magnitude of the electric field is at a certain point given in Cartesian elements and given a electric potential. So to find the electric field, we know that this is negative dV over dt. So in this case, we're going to take, or rather than dt, just put dk, right? Because we're going to use our separate variables for this. So if I were to write this in a better to understand way, we're going to take the partial derivatives of each element. For I direction, move this negative to the outside. dy in our j direction, and in our k direction. So what this means is that when we plug this in for our v, we're going to derive with respect to each of the variables here. So if we start out with deriving with respect to x, this becomes 5yz squared, and then that's our I direction. And this is plus 5 in our, xz squared. So just basically treat all the other variables as if they were constants. So for example, when I did the first term, I was treating x like the only variable and y and z like constants. So if you had like 2x, the derivative would be 2. So that's why the x goes away, because we're just leaving our 5, y, and z. And now that we actually have z with a power to it, we can bring that power down. So that's 10, and then that's x, y, z in our k direction. It'll start to make more sense. So now we're going to take these points and we're going to plug them in for each of our x, y, and z components within here. So this is negative 5. Our y component is 6 in our point, and our z component is 7 squared. And our I component, this is 5 times our x, which is 1.7. Oh, sorry, this is negative 6 times our z squared, our j direction. And this is 10, and our x, our y, and our z. Okay, so when we write this all out, this is negative. It's negative 30 times 7. It's negative 210 I. And this is 5 times 1.7 times 7. It's 59.5, positive, j direction. And this is 10 times 1.7 times negative 6. times 7, and this is negative 714 in our k direction. So now we want to find the magnitude of this. So now we can find that. So let me just distribute those negatives. Won't matter anyways when we square it, but just good practice to be consistent. So now to find our magnitude, we are going to do 210 squared plus negative 59.5 squared plus 714 squared. So let's calculate that. 210 squared plus 59.5 squared plus 714 squared. And then when we take the square root of this, this becomes 746.616. Okay, that is not the answer that I got. Let me check to see where I went wrong. Oh, yeah, sorry. I forgot to square the 7 when I put it in to calculate. So I hope you will backtrack with me. I apologize. Okay, let's go back. Let's actually calculate this correctly this time. Okay, so this is 49 times 30. This is negative 1,470. And for 5 times 1.7 times 49. And this term here is meant to be 416.5. And when we distribute those, that is, this is minus 416.5 in our j direction, plus 714 in our k direction. And now when we find our magnitude, that's equal to, so that's 470 squared plus negative 416.5 squared plus 714 squared. So let's try this again. So this is 1,470 squared plus 416.5 squared plus 714 squared. And we take the square root of this. There we go. There is our answer. This is 1,686.46 newtons per coulomb. In this case, volts per meter. Right, so don't use that units. Right, and this is our final answer. Okay, last question. So this question is having us take the flux at different locations of two concentric conducting spherical shells with reference to a graph that is given to us on the right side. So it wants us to find our flux at 3 different points: at the center, in between at A, and outside both at B. So if you start with the center, you're just going to deal with the center on its own. Once you get to A, you have to deal with whatever flux is produced at A, and look at whatever is produced at the center. And B takes into account all 3. So if we match these points on our diagram, we see that we start here, where this is a function of our changing radius. So the smallest radius is going to be our center. So that's how we know that's where our first point starts. The next slope is going to be A. Then when it goes back down is B. Okay, so let's start with our first one. And we're going to be using the right side of our Gauss law equation. So let's start with our red. So we use our flux is equal to Q enclosed over our epsilon naught. And we want to find what our charge is. So if we move things around, our charge becomes flux times E naught. So we're going to use our graph to find what our flux is. So we're given a scale on the side where our flux at S is equal to 6.0 times 10 to the 5. And at this point, we are at, so out of 10, we are at, so each one has 5 blocks in it. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see that's 9 out of 10 for S. Or, sorry, for 2S. 2 flux S. Or you can say this is our flux S plus 4 over 5. Flux S, which would then be equal to, so this is like saying 5 over 5, so that you could just say 9 over 5. Right, so let's use that one. And that's going to represent our flux. So this is 9 over 5, and let's just put our flux right in there. And epsilon 0 is a constant, times 10 to the negative 12. And this is going to give our first enclosed value. So this is 9. 9 divided by 5 times 6 times 10 to the 5 times 8.854 times 10 to the negative 12. And this is 9.5 times 10 to the negative 6. And I forgot to put a negative value in for this scale, so this would make it negative. And this is in coulombs. So that is our first part out of the way. And if you remembered, I mentioned for A, we need to calculate A on its own and then the net, including the central one. So we're just going to start with the enclosed on its own. So this is, and that's equal to, so now we are at 4/5 positive 6.0 times 10 to the 5. So that's our flux scale. And this is 8.854 times 10 to the negative 12. So this is 4 divided by 5 times 6 times 10 to the 5 times 8.854 times 10 to the negative 12. And this gives us 4.24992 times 10 to the negative 6. Okay, but we are not quite there yet. So in order to find our net at A, we have to take our enclosed charge and subtract our first one, which is Q central. So let me just, right, that's what we found up here. So when we do that, we get 4.249 minus, then our value was negative for our first question, so this minus negative 9.562 times 10 to the negative 6. Forgot to put that in for the blue, but just imagine that it's there. So then our total becomes, so then this is plus 9.562 times 10 to the negative 6. And this will be 13.812 times 10 to the negative 6 coulombs for our net charge. All right. Okay, so now for B, we're going to use all three. So let's calculate Q enclosed for B on its own. And this is equal to, so we are at negative, so this is at 2/5 of negative of our scale times 8.854 times 10 to the negative 12, and this is equal to 2 divided by 5 times negative 6 times 10 to the 5 times 8.854 times 10 to the negative 12. And this is negative 2.124 times 10 to the negative 6 coulombs. And to find our total, we would have to do our Q enclosed at B, and then minus what we got at Q A net, and minus our central one. Actually, no, at net that already includes both of them, doesn't it? Sorry, no, I lied. I was right the first time. Minus our Q central. Okay, and when we do this, so this is negative 2.124. I'm going to do it without the times 10 to the negative 6 just to make it more concise. And this is minus 13.812. And this is minus negative 9.5623. And this gives us, so that's negative 2.124 minus 13.812. That's plus 9.5623. And indeed, this gives us negative 6.3737 times 10 to the negative 6 coulombs. And that is correct with the answers that we got. Okay, that brings us to the end of the practice problems for this unit. I hope you enjoyed, and I hope you learned something. And I hope your skills have strengthened for questions that involve graphical analysis. So always just think about how they play in with each other and how you can use those given variables to your advantage. And be careful when you're given a certain scale. And yeah, thanks for watching.